Hello and welcome back to Wheel Analysis. And as always, I want to thank all the nice people that support this channel on Steady or PayPal. Today's part 7 is about Cauchy sequences and completeness. For starting this topic, let's recall that we already considered sequences with a special property, namely convergent sequences. Which means there is a number A such that the sequence members here get arbitrarily close to this number A eventually. You already know the formal way to say this, which is for all epsilon there exists a capital N, such that for all indices n greater than this n, the distance between A and AN is less than the given epsilon. Now the problem with this definition is that you need to know the limit to show convergence, simply because we measure the distance to this A. Hence there is a different idea or a different property a sequence can have, which does not need such a number A in the definition. For this, let's look at the number line again and at a sequence which should converge. So here we have A1, A2, A3 and so on. And the sequence members accumulate here, so there should be a limit here. However, we don't want to use this limit to describe what happens here. Indeed, what happens here is that the sequence members themselves get closer and closer to each other. Hence what we want is that the sequence members lie arbitrarily close to each other eventually. So everything is about the distance you can measure between two sequence members here, which is the absolute value of AN minus AM. And then this should be less than epsilon we choose at the beginning. Therefore, the formal way then reads: for all epsilon greater 0, we find a capital N, such that for all indices called n and m afterwards, we have that the distance between the sequence members is less than epsilon. And now a sequence with this property we call a Cauchy sequence. Okay, so let's put that into a definition. This is exactly the definition you might have already seen in my Start Learning Wheels series. There I also showed you the important fact that for a sequence of real numbers, we have that being a Cauchy sequence is equivalent to being a convergent sequence. The proof of this direction you can see in part 2 of the course, and the other one is exactly the completeness axiom. So the completeness axiom tells us that there are no holes in our complete real number line. Now what you really should remember is when we work in the real numbers, we don't have to distinguish Cauchy sequences and convergent sequences. They have different definitions, but for the real numbers they mean the same thing. Therefore, we are able to use the one or the other definition depending what is useful in our context. And soon we will see that the definition of the Cauchy sequences make a lot of things easier. However, before we apply this in examples, let's discuss another important property. It's called Dedekind completeness and a property for subsets of the real numbers. If M is such a set and also bounded from above, then we know the supremum exists. So there is a least upper bound as a number in R. Please recall that we defined the supremum in the last video. And maybe not so surprising, we have the same thing for the infimum as well. So if we have a set that is bounded from below, then the infimum exists as a real number. Okay, let me explain how we can prove this statement. And I think it's enough to give you the idea how to do it for the supremum. For this, let's consider the number line and the set M on it. Then we know we find an upper bound for the set M, so let's choose one and call it B1. On the other hand, let's choose any element in the set M. And this one we call just A1. Now the idea is that we then go to the point that is exactly in the middle of these 2 points. And this one, of course, I now call C1. So we just calculate the sum and then we divide by 2. So in this case we find this middle point somewhere here. Of course, the idea is that by doing this calculation we get closer to this point, which is the supremum of M in the picture. Therefore now I explain how we get the whole sequence, which gives us an approximation of the supremum. Okay, you might have already seen we can have 2 cases for C1. Either it's still an upper bound like B1 or not. In the first case we just have a smaller upper bound, so a better one, so we can just substitute B1. Or to put it in other words, we introduce B2 to be the new upper bound given by C1. On the other hand, the left hand side we don't have to change, we just stay at A1. And then afterwards we do the same thing again, now with A2 and B2 to define the middle point as C2. In this case you then would see that the middle point lies left to some points of M. Therefore then we have to think what we do in this second case. Now as I said, here it is possible to find a point X in M which is larger than C1. Then of course this new larger point should be our new A2. So with this we shifted the left point to the right. And then we don't need to change the right hand side with B1. Now having this, we have the whole procedure how we can form the sequences. So in general, when we have AN, BN, we define Cn. And then, as before, we just define the two next numbers here. So this is a recursive definition, which gives us two sequences AN and BN. And the sequence members BN are always upper bounds, which approximate the supremum. Therefore, the only thing that remains to show is that the sequence Bn is indeed a Cauchy sequence. However, this is not hard to see because we have the following estimate. Namely, for two indices m and n, where m is greater than n, we can calculate the distance Bn to Bm. I use the absolute value here, but honestly we don't need it because Bn is greater or equal than Bm. And now the distance gets larger when we substitute any a for this Bm. And the best a we can choose would be a with index n. Now we know by our construction with the middle point that we always cut the distance in half. Therefore we know that this is 1/2 to the power n minus 1 times the starting distance B1 minus A1. And now this whole number here we can get arbitrarily small. This is what you can show, and then you can formalize the conclusion that Bn is indeed a Cauchy sequence. And then the last step is just using the completeness axiom to show that Bn is a convergent sequence. Also, the only possibility for the limit then is the supremum of M. Okay, so that's the overall idea of the whole proof. The missing details you can easily fit in. However, now knowing that the supremum and infimum always exists has an important application. We immediately get a nice criterion to show convergence of a sequence. If the sequence AN is monotonically decreasing, which simply means that each sequence member is less or equal than the predecessor. And if the sequence is also bounded from below, which simply means that the set given by the sequence members has a lower bound. Then we can finally conclude that the sequence is indeed a convergent sequence. There you see, this is a very useful criterion because you only have to check two properties, which could be easier to check than the definition of convergence. In this formulation, you might already see we use the existence of the supremum of this set. However, if we use the existence of the infimum, we get another criterion. Of course, it's very similar, there we just need a monotonically increasing sequence which is bounded from above. And then we can also conclude that we have a convergent sequence. Okay, and then in the next video I show you some examples for this application. Therefore, I hope I see you there and have a nice day. Bye!